Hello students, I am Rajiv Jha and this is my 7th video on question and answer on electrical machine. And in this video you have learned about hunting and damper winding in alternator actually. And this is the most and very interesting topic on alternator. So I hope you will like this video and so let's start. So here our topic is hunting and damper winding. Our first topic we will start with hunting. What is hunting actually? So when sudden disturbance occurred on rotor, then rotor start hunting or searching for new equilibrium position. This phenomena is called hunting. That's simple it is. Okay. So hunting is just like you can say whenever the disturbance is occurred. So in at that time the acceleration is happened into the rotor to find out or to hunt the new position which is suitable for their stability. That means at that point the del or you can say the load angle should be constant, or the second condition is PE, that is the electromagnetic power equal to PM or the mechanical power or shaft power if we neglected all the losses. Okay, so these two conditions should be satisfied duration of you can say hunting. So duration of hunting or searching, what rotor search for? Rotor search for del equal to constant, and second one is a position which have del equal to constant value, and second one is PE, that is the electromagnetic power equal to the mechanical power. So whenever rotor got these 2 points, then it stop that position or it break the phenomena of hunting, or hunting would be eliminated. Okay, so here you see what is the causes of hunting. Okay, so causes of hunting is, first is load, sudden change in load. Second is sudden change in supply system. Sudden change in load, such sudden change in supply system, sudden change in field current. So these type of sudden changes is one is you can say the prime reason for the hunting actually. And then after we see there is some load, okay, which is the you can say which have contained harmonic torque actually. So just like you can say if I talk about the compressor, so compressor is the wonderful example of containing harmonic torque. Okay, then second one is crank. Okay, so crank is also you can say containing harmonic torque. So these two example through which we can say this is the load through which the hunting is occurred. Okay, instead of these load, if sudden change in load is occurred and sudden change in supply system or sudden change in field current, then also we will you can say get a hunting, okay, in the synchronous machine. So from this diagram actually we get to know what is hunting. Okay, from this way you have seen this is the power equation where VTEF upon XS is constant value. How it is constant? You see, from O to A to B, all the value of E will be constant, and in this way you also see from OAB whatever the reactance is also constant, and duration of this OAB, the terminal voltage is constant. So what is OAB? OAB is the position. In O, the terminal voltage and EF both are in same phase. Okay, so that means there is no losses, so del equal to 0 or del is constant. In that case PM, there is no shaft power equal to PE. So this is the equilibrium position actually. After that, whenever the disturbance is occurred, the del 1 is changes, or you can say suddenly load is changes, so in that case the load angle is also changes. So in we will get a current called IA1. Through that current we will get a terminal voltage, and the reactance we will get IA excess, or reactance drop, synchronous reactance drop, we will get a IA excess, through which we get the point terminal voltage over here. So from the point O to A, it is not stopped with A, or it is not the gain, it is not fixed with the del 1 position or load angle del 1 position. It start moving due to their inertia of the rotor. So it the acceleration happened between O to A, then A to B, then B to A, and A to O. So these type of acceleration actually happened like this. Okay. So through this oscillation, we can say this is the hunting phenomena, through which it find out the position where del would be constant, and where PE equal to PM. So in deep you can say, or in deep analysis, we have seen in this video how the hunting and what is the procedure will be going on duration of the hunting actually. So our next slide is, yes. So here you see the I will what I talk about hunting process. So here you see initially this is the graph of omega. Omega is the, you can say, speed, and t is the time. Okay. So initially we see, before going to the discussion, try to remember these formula. So this is the formula, this is the, you can say, swing equation. That is the most important equation if you want to know hunting. So you should have to know the swing equation actually. So that is the most important formula for understanding the hunting process. Second one is this, d del upon dt equal to delta omega, or you can say the change in speed. And this one is well known, that is a active power equation, ve equal to vt into ef upon xs into sin del. So at point A, what happened at point A? Okay, at point A, this is the synchronous speed. So that means at point A, before a point A, there is a equilibrium position, rotor are existed, rotor was in equilibrium position actually before point A. So at point A, what happened? System operated at steady state before point A. Okay, the first thing. Second one is PS equal to PE equal to P max sin del. Okay. फिर suddenly at point A, if you talk about the point A, suddenly input power or shaft power is given. Okay. So point A, at point A, before point A, what happened? We will talk about. So before point A, PM, that is the soft power, equal to, or mechanical power equal to PE, and you can say del equal to constant. These two conditions occurred before point A. So at point A, what happened? Suddenly we give the input power shaft. Yeah, input shaft power. Okay, that means suddenly PM is increased. So here you see, if PM is suddenly increased, so in that case, what happened? There is a condition of acceleration. That means the rotor will start to accelerate. Okay. Then here d del upon dt, here we see what is the condition actually when we increase the PM. So when we increase the PM, the rotor is accelerate. That means the rotor velocity is increasing. Okay. And d del upon dt equal to omega minus omega s. So if omega is increasing, that means d del upon dt equal greater than 0. So what is the mean? That actually from this way we can say the value of del will be positive, or value of del will be increased. So the value of del increase, that mean the value of PE is increases, because initially the value is PE is not increases, the value PE is 0. So it is increases because del is increases. How the del is increases, we already discussed actually. So according to Singh equation, PE is not changed initially at the point A, but we will talk about point A to B. Okay, A to B the PE is increases initially, but at the point of instantly the load is not changed. Whenever the input power soft is given, the load is not changed. So that's why there it is only, you can say the PE is only, PE is not changed at that time, at the moment when we talk about the point A. Okay, so what about the point A to B? Okay, this point actually we will talk about this point. So when it goes to A to B, in that case PS, or you can say the soft power or mechanical power, is greater than electrical power. That mean in this case PA is greater than 0. That means this is the case of acceleration. Okay, then if it is accelerate, then omega, which is the rotor velocity, should be increased. So in that case what we say, we we know d del upon dt, sorry, d del upon dt equal to omega minus omega s. So here we can say, in this case, at point A, at point A, at point A, what is the condition? Omega equal to omega s. But here because we are moving from point A, so here d del upon dt is equal to, which is equal to omega minus omega s, that is omega is greater than omega s. So in this case d del upon dt is positive. So rotor angle is, or you can say rotor angle, it is rotor angle. So rotor angle is increased. Okay, so rotor angle is increased. So speed must greater than synchronous speed. Okay, so here you know the speed is greater than synchronous, this is the synchronous speed. So here you see the speed is greater than synchronous speed. If you talk about the synchronous speed here, if we let 1000 rpm is synchronous speed, then in this case there is something around something between the speed something speed between of 1000 to 1500 rpm. Okay, so it is almost, you can say, uh, above to the synchronous speed. Okay, so here the first condition A to B is PS is greater than P. You know how it is, PS is greater than or PM is greater than P, because whenever we apply the at point A, the PM is increased. So here we can say PS is greater than PE, so the acceleration is occurred. So rotor is going to be accelerated. Rotor speed increases. Okay, then rotor, you can say change in rotor angle is getting positive. That means d del upon dt is positive. So del should be increased. Okay, so these type of thing happen duration of AB. Next we will go actually at now we get the point of point B. Okay, what happened in point B? In point B, PS, or you can say soft power, is equal to PE. Okay, in this case the acceleration is 0, acceleration power is 0. So no acceleration occurred during this. So here you can say d del by dt equal to omega minus omega s. So the value of omega is increased, because value of omega is here we know it is almost 1500 rpm. So and this one is 1000 rpm. So d del upon dt, d del upon dt is positive. Okay, so rotor angle still increases. That means rotor angle still increases in this position. So if we know the rotor angle is increases, so PE, we know PE equal to VTEF upon XS sin del. That means PE is also increases duration of this. So duration of this or at the point PE, at the point B, PE is increases. That is the main outcomes coming from this. Okay, next is, yes. So now we are going to be discuss what happened between of B to C, duration of when the rotor going from the B to C position. In this position, actually we know PE greater than PS1, or you can say the mechanical power or soft power. So whenever this happened, actually that means d square del upon dt square is negative. So what is this mean? This means there is a deceleration occurred. Okay, deceleration occurred. That means rotor will decelerate, and rotor will decelerate means omega is the value of omega will be decreases, but value of omega will be decreases, but because of omega equal to 1500 rpm, when we let about it actually, so in this case again we will get d del upon dt is positive. Okay, so that means del is all again increases duration of this one, duration of B to C, del is again increases, and PE is, you can say, increases to PM. That's why that deceleration occurred. So here in this way B to C, there is two most important thing: decelerating occurred and rotor angle again increases. That two things happened here. Okay, so next one is what happened when will be we will be in point C. Okay, when we reach the point C, actually in that case we see PE, that is the electromagnetic power, is greater than PS, that is soft power. In that case we see we have faced the deceleration actually, or you can say the acceleration is negative. Okay, so here we see d del upon dt. In the case of C point, d del upon dt, you see both are 0 because omega equal to omega s. Here you see when we reach the point C, the value of omega r equal to omega s. So d del upon dt equal to 0. That means d del upon dt equal to 0. That means we will get a del a constant value. So after that we will not increase the value of del. So then after the value of del will be decreases. Okay, so from C to above, from C to you can say the C to for uh, further condition, we are not going to increase the del, because if we increase the del, the you can say the synchronism should must be lost, and it is unstable permanently. Okay, that's why the value of del will be decreased from the point of C. From the point C, the value is decreased. So because of this, the value of del is decreases, the reversible process. So it start back from C, then B, then it goes to A. So through this, and this process repeats again and again, at last it stop or stable at point B or any further point where the hunting process will be where the equilibrium will be get. Okay, at that point the process will be stopped. So this phenomena is called the hunting. Okay, so this phenomena is called the hunting. Okay, so what is the way through we can eliminate the hunting? So we can eliminate the hunting by three methods. Okay, first is by using of flywheel. That means whenever the excess energy is supplied, we have to store that energy and supply it whenever it needs, whenever system needs. Second one is by designing machines such that it has suitable synchronizing power coefficient. So what is synchronizing power coefficient? Synchronizing power coefficient is the stability factor. So we have to design, we have to see, we have to maintain that designing part in such a way that we have got a suitable synchronizing power coefficient. So if we have a suitable synchronizing power coefficient, then hunting is already eliminated. Okay, then third one is, and you can say the most important term is by using of damper winding. So by using of damper winding, we eliminated the part of hunting. Okay, so let's discuss what is damping. So this is, you can say, the structure, or you can say the damping actually. This is called, this is the rod of damping. It is short circuited actually. It is short circuited. Okay, here you see this is the bars, damping bars. Okay, this is the damping bar. It is short circuited like this. Okay, it is a short circuited like this. So what is damper winding? What is actually damper winding? Damper winding is a winding which is used to damp out the damp out the disturbance which is occurred at the rotor side. Okay, any disturbance which is occurred at the rotor side will be damp out through the damper winding or eliminated by the damper winding. So damper winding actually, our first question, a lot of students have asked about damper winding made up with high resistive material. Why? Okay, we know which material damper winding. Damper winding is made up with aluminium, brass, okay, copper. So these are the high resistive materials actually. So why we use the high resistive material? Because we know actually, here time constant actually, we know the whatever the hunting or whatever the disturbance occurred at the rotor side, we want to you can say eliminate that rotor as soon as possible, as soon. That means we want eliminate this with a fast response. That means within a time, within a millisecond or microsecond, we want to eliminate that disturbance. Okay, so that's why we know damper winding or any winding, any coil is just a form of inductive load. So if we get the time constant, then we can say it is equal to L by R. L is the inductance, R is the resistance. So if we increase the resistance, then time is automatically decreases. Okay, so that's why we use the high resistive material. We use the high resistive material for making or made up for making damper winding. So that is the important question. Even in viva or interview or you can say after in the PSU interview, so lots of interview you have seen, this is the very most common actually question asked in every PSU interview, or you can say MTech interview. if you are go for the IIT. So in that case you have seen this is the most common question, not important. I want to say, I'm saying actually it is not important, but it is most fundamental question actually. Okay, for the interview purpose. So try to remember it. So here you see how the how that what condition we will use the high resistive material for making a damper winding. So here you see what is the use of damper winding. So use of damper winding, so alternator and synchronous motor, okay, in both case the use of damper winding are different, but the most common is hunting. So eliminate the hunting process. In the, if we talk about the alternator, the first is eliminate the hunting process, second is to suppress the negative sequence field. So what is in this video we only talk about the alternator, the use of alternator, the use of damper winding in alternator actually. In this video we only talk about this. Okay, eliminating of hunting in the synchronous motor we will talk about. There is a two reason we use, why we use damper winding. First is eliminating the hunting, second one is the to start the synchronous motor. So through this way we can understand use of damper winding. Okay, so here what is the condition, stable condition of alternator. So what is the stable condition of alternator actually? So in we know actually EMF induced in the rotor bar is because of induction action. So okay, so what is the stable condition? Stable condition when EMF is 0, when in damper winding we didn't get any EMF, because in stable condition both have the same speed. So the relative speed between of stator and rotor is 0. So in damper winding, because it is a short circuit and behave like a induction motor or induction machine, so in that case the winding is short circuited here, you see. So all the EMF is generated due to the difference between the stator mmf and rotor mmf, or you can say the difference between the uh, rotating stator rotating mmf and you can say rotor rotating mmf. So in this point you see the rotating stator rotating mmf, the speed is ns, and here the rotor rotating mmf, the speed is ns. So their speed is constant, so there is ns minus ns, because they are in the same rotation in the same direction actually, they rotate. So ns minus ns equal to 0. So there is no EMF generated here, so this is the condition of stability or stable condition. So due to hunting or any other disturbance, what happened then? Due to hunting or any other disturbance, okay, disturbance, hunting or unstable condition, what happened? Rotor start oscillating around its position. So what happened? Whenever the rotor will start oscillating around its position, okay, so here you see it is not in the synchronous speed. So when the rotor is moving actually, when the rotor is moving, or you can say start oscillating, then the speed of rotor is change. It is not ns, actually it is nr. So the speed of rotor is changed. Now ns minus nr, the difference is occurred or difference is shown here at the damper winding. So we will get the EMF. Okay, so it is not in the synchronous speed either. Okay, maybe there is a synchronous speed in rotor, it is not the synchronous speed, either it is increasing or decreasing with ns. Okay, not only decreasing or not only increasing. Okay, either ns sorry, yeah, that is nr, either nr is increasing with the ns or decreasing with the ns. or you can say either nr is greater than ns or nr is smaller than ns. Anything happened after disturbance we do not know, but it is not equal to ns. That I know actually. After the disturbance, rotor speed is not equal to the synchronous speed. That is I know actually. Either it is greater than synchronous speed or smaller than synchronous speed. Okay. So the next is EMF induced in the rotor. So we know the EMF induced in the rotor bar, or you can say the damper winding, is occurred due to the, you can say, relative speed between of stator and rotor rotating mmf. So because of the, here you see there is a relative speed, so that's why the emf is induced on the rotor or damper bar. Okay, so emf is induced, so you can say due to the Lenz law, we know due to the Lenz law we know causes opposes its own reason, or you can say the Lenz law say कि whatever the effect opposites its own cause. So what is the cause? Cause is ns minus nr. Because of this the emf is generated. So what emf do? It opposes the ns or it can it can eliminate the ns minus nr or relative speed. So it's going to, or nr is going to the, nr wants to be ns actually. So from this way it eliminates the ns minus nr, or it from this way it eliminates, or it gives the ns minus nr equal to 0. Okay, so as I told you, there is a two condition: either n is greater to, or you can say the rotor speed is greater to ns, or rotor speed is smaller to ns. So whatever the condition, so we will have to justify here. First condition is if rotor speed is greater than synchronous speed. Okay, so rotor speed is greater than synchronous speed, then it produce induction torque, that is Td. Okay, so if we increase the rotor speed is increases with the synchronous speed, in that case ns minus nr, or you can say it ns minus nr is negative, or you can say nr minus ns will, we will get positive in the in the opposite direction of ns. Okay, in that case the td, actually there is a there, because of Lenz law we want to compensate the relative speed between of stator and rotor mmf. So due to this it produces the induction torque. Okay, that induction torque is depend on phi a and ia. That means armature flux and sorry, ia nahi, it's a id, it's a id, damping torque, damping current, or current in damping bar. Okay, so here if so here what the role of td, or you can say the damping torque. So through damping torque it opposes the nr minus ns, and it wants to nr to decrease actually, and give, and it wants to nr to decrease, and it wants to nr to decrease till the ns is achieved, or synchronous speed is achieved, because here we talk about nr is greater than ns. So nr is decreased till the synchronous speed, it synchronous speed is achieved. Okay, so from this way it handle the things actually. What is the condition? If nr is greater than ns, then because of Lenz law the torque is produced that is proportional to the phi a and id is the current in the damper winding. Through the because of this damping torque, the rotor speed will be decreases till the synchronous speed will get. Okay, the second condition is, we will see the second condition. Second condition is when n, or you can say the nr is smaller than ns. So in this condition, all we will again get the damping torque. Okay, or that damping torque, it opposes the cause, so it opposes the ns minus nr. That means it increase the rotor speed till the synchronous speed will get. So nr here, the nr is increases till the rotor speed or synchronous speed will get. Okay, so from this way we have seen how the you can say the phenomena of damping occurred. Okay, so or you can say how the hunting is eliminated through the damping actually. The second phenomena is, here we see how to suppress the negative phase sequence field. Okay, whenever the you can say any fault occur in alternator, so through the fault rescue theorem we can see we divide the faulted mmf into a three part. First is positive phase sequence field, second is negative phase sequence field, and third one is you can say zero phase sequence field. For you can say through this way we can make a calculation very easy to detect the fault current or all the phenomena of stability, or all of the you can say phenomena of how the MVA is got from that, uh, or you can say short circuit MVA we will get from. So these type of calculation can be or could be easy if we consider the Fortescue theorem. Okay, so in case of unstable instability. Okay, so how to suppress the negative phase sequence? So first of all we will have to see actually how the what is the positive phase sequence and what is negative phase sequence and what is zero phase sequence. So this is the positive phase sequence. Here the sequence is r y b. Okay, and the direction of the rotor, or it is the same direction of the rotor actually, so it is a clockwise. Okay, then we talk about negative phase sequence. So this one is negative phase sequence. Here only, here we change the two phase r y and b actually to exchange their position. So this one is called the negative phase sequence. Okay, the third one is, this one is the third one, this is called the zero phase sequence. So in zero phase sequence there is no rotating mmf or rotating field we have, there is no rotating field so generated in zero phase sequence. So the problem is because we know positive phase sequence is just like you can say a normal phase sequence which we should have to follow. So the complication occurred due to the negative phase sequence. So that's why it is important to suppress the negative phase sequence field. So how it is possible, how we suppress the negative phase sequence? So by using of damper winding we suppress the negative phase sequence. So here we see there is a normal rotation actually at stator mmf field. It rotate at synchronous speed ns, and rotor is rotate at synchronous speed ns also. Okay, so due to the positive phase sequence field, the stator field you have seen here rotated at synchronous speed in clockwise direction, and due to the negative phase sequence field, the the stator field rotate at anti-clockwise direction. So here we will get a, you can say the relative speed, just because of we know any phenomena happened in damper winding or any EMF is generated in damper winding is due to the relative speed between stator mmf or stator field and rotor field. Between of stator field and rotor field, there should be a relative speed occur. Okay, due to this we will get the EMF at the damper winding. So because of this, so first we see, when we talk about the positive phase sequence field, then we see their relative speed of positive phase sequence ns and the rotor is field speed ns, both are in the same direction. So ns minus ns equal to 0. So their relative field is relative speed between of their positive stator field and rotor field will be 0 here. Okay, so then we see the relative speed between rotor field and negative sequence field mmf. So if we see the you can say the their relative speed between of stator negative sequence field and rotor field, then we will get the relative speed is ns plus ns equal to 2ns. So because of this relative speed is so high, so that's why we will get the emf, the large value of emf, and that large value of emf strongly opposes the flow of negative phase sequence, because uh, due to the Lenz law we know causes opposes its own reason. So reason is ns plus ns equal to 2ns. So reason is negative phase sequence field mmf. So that's why causes opposes in own reason. So that's why damper winding whatever so damper winding start flowing its mmf through that emf. It start flowing that mmf, which opposes the negative phase sequence field. Okay, so we will get the another mmf that is you can say support that is in the clockwise direction, and its speed is ns. So through this way it opposes the negative phase sequence field mmf, and it cancel out. So from this way is suppress the negative phase sequence field. So due to damper winding emf, this field, or you can say that this mmf field is generated in the clockwise direction, and it opposes the negative phase sequence field, okay, which is in the direction of anti-clockwise direction. So in their opposite, their mmf cancel to each other. Okay, so they suppress. So from this way damper winding suppress negative phase sequence field. Yes, and so from this video we have learned damper winding and hunting process. Okay, and I hope you like this video, and if you have any doubt please comment. Thank you.